Hello everyone, welcome to Planck Academy. In this video, we are going to discuss about reactive intermediates, namely free radical, carbocation, carbanion, carbenes, nitrenes, and benzynes, which are generally short-lived in between reactions. These species often occur as intermediate in organic reactions. Now, let us discuss a few aspects of such reactive intermediates. Consider a covalent bond between A and B. The breaking or cleavage of a covalent bond can take place in three ways. In the first type of cleavage, the bond is broken symmetrically, so each atom separates with an odd unpaired electrons, which is represented using a fishhook arrow like this. We use this arrow only when one electron, not the whole bond, only when one electron moves from a bond to an atom or group of atoms. On the product side, we have free radicals. So homolytic cleavage or a symmetrical cleavage breaks a bond in such a way that the reaction will give rise to free radicals. This is the first type of cleavage. The second and third type of cleavage is heterolytic cleavage, in which the bond is broken unsymmetrically to give rise to electron-rich and electron-deficient species, that is anions and cations as shown here. This type of cleavage is represented using normal arrows, which indicates that the whole bond itself is shifted towards an atom. These ionic species are highly reactive. Instead of A and B, when a carbon carries a positive charge, it is called as carbocation, and when it carries a negative charge, it is called as carbanion, which we will be discussing later on in this video. Next, we will jump on into free radicals. Free radicals are paramagnetic species containing an atom or group of atoms with one or more odd and unpaired electrons. If a reaction is initiated by free radicals or involve free radicals as intermediate, then the reaction is called free radical reaction. For instance, consider the reaction in which chlorine radical reacts with methane H3 in the presence of sunlight to give methyl radical. This is 3. Please don't mind my handwriting. Plus HCl. This here is methyl free radical, and the chlorine radical attacks the hydrogen to form HCl. The carbon in the methyl radical is sp2 hybridized, which is shown by carbon in its excited state. This is a 2s orbital of carbon, which has one electron. Since it is the excited state of carbon, the electron here, one of the electron in the 2s orbital will jump to 2p. We have 3 electrons each in 3 of the 2p, 2px, 2py, and 2pz orbitals. We have 3 hydrogen in the methyl radical, so these 3 hydrogen will make a bond to these hybridized orbitals, which is sp2 hybridized orbitals, and we still have a lone unpaired electron in the unused p orbital here. Now let's see the structure of simple alkyl radical. In this picture, the 3 bonds attached to the carbon atom lie in a single plane, with a bond angle of 120 degree each, which sums up to 360 degree. Whereas the unused p orbital lobe, which contains an odd unpaired electron, is projected above and below the plane. For better understanding, I created this model in 3D. This is a 3-dimensional structure of simple alkyl radicals. In here we see that the unused p orbital lobe, which is shown in blue color, is projected above and below the plane, and we have the first bond here, which is on the plane of the paper, and we have the second bond here, which is slightly projected towards us, and we have the third bond, which is behind the plane of the paper, which is projected behind the plane of the paper. And the bond angle between these 3 bonds is 120 degree each, which sums up to 360 degree, and these 3 bonds lie in a single plane like this.
The evidence which supports the planar structure is that when plus 1-chloro-2-methyl-butane is subjected to sunlight in the presence of chlorine,
we get plus or minus 1,2-dichloro-2-methyl-butane, which is a racemic mixture. In this reaction, we clearly see that the optical property of this compound is lost in this compound since this is a racemic mixture. To understand this evidence properly, let's take a look at the mechanism of this reaction, in which the chlorine radical here attacks the hydrogen here to form 1-chloro-2-methyl-butyl radical. This is a flat compound with sp2 hybridized central carbon. Now let's take a look at the three-dimensional structure of this compound. This compound here is the structure of 1-chloro-2-methyl-butyl radical. As we can see that the three groups are projected in different directions like this. One facing towards us, one facing away from us, and one on the plane of the paper. The lone unpaired electron on the unused p orbital is projected above and below this plane. Now the chlorine radical can attack the carbon in two ways, either above the plane or below the plane like this. Two attacks are equally possible, so we get equal mixtures of two compounds. One compound rotates the plane polarized light in one direction to some extent, and the other rotates the plane polarized light in the opposite direction to the same extent, so they get nullified, and we have an optically inactive plus minus 1,2-dichloro-2-methyl-butane as product. And this product can be produced only when this radical here has a planar structure, and the unused p orbital lobe is projected above and below the plane. This evidence is fair enough to prove that all the simple alkyl radicals have a planar structure. Next, the stability of free radical increases in a trend like this. The methyl radical is less stable than the primary radical, and the primary is less stable than secondary, and the secondary in turn which is less stable than the tertiary radical. So the tertiary radical is the most stable radical and the methyl radical is the least stable radical. The above order of stability can be explained through hyperconjugation. If you didn't check out our previous video on hyperconjugation, please do check it out. I'll provide the link in the description below. We say that the tertiary radical is more stable because it has more hyperconjugative forms than secondary and primary. As we can see here, the tertiary radical has 10 hyperconjugative forms and the secondary radical has 7 hyperconjugative forms and the primary has only 4 hyperconjugative forms. So we say that the tertiary radical is more stable. Allyl radical like this and benzyl radical like this are more stable than simple alkyl radicals due to increased stabilization because of resonance. And if you didn't check out our previous video on resonance, please do check it out. I'll provide the link in the description below. Next, we'll see about carbocations, in which the carbon has a positive charge and has 3 bonds attached to 3 different atoms or a group of atoms. It has a trigonal planar structure with the sp2 hybridized central carbon, which is this, and represented by in its excited state has a 1 electron in 2s orbital and has 2 electrons in 2px, 2py. This carbon here is a trivalent carbon, so these bonds may attach to a hydrogen atom or any other alkyl groups, and each of the atoms or group of atoms make a bond with these electrons here. The unused p orbital here remains vacant without any electrons. That's why we represented a plus here, which means that there is no electrons in the p orbital, in the unhybridized p orbital. Now let's quickly see the formation of carbocation. Consider a tertiary alcohol like this, and these bonds may be attached to a hydrogen or any other alkyl groups. Now if a H plus attacks this OH group, we get oxygen attached to 2 hydrogens. Oh, so this is hydrogen, and we get a positive charge on the oxygen here. On the next step, we eliminate this H2O. So the electron which belongs to carbon here also get eliminated along with the bond, and it's removed as water. As a product, not as a product, as an intermediate, we get a carbocation. Now let's see the three-dimensional structure of this carbocation. This is a structure of three-dimensional structure of carbocation. As I told you before, it has a trigonal planar structure with the sp2 hybridized central carbon, which is represented on the center, and we can see here the three bonds are projected at 120 degree to each other, and three bonds lie in a single plane like this. As we can see in this direction, three bonds lie in a plane. So it's clear that the three bonds lie in a plane, but the projection of three bonds is different, which are lying in 120 degrees like this. And we see that the one bond lies in the plane of the paper, and one bond is towards us like this, and which is represented by the wedge representation, and the third bond is facing away from us, which is on the back side of the plane of the paper like this. And we have a unused p orbital lobe which is projected above and below the plane, which has no electrons in it, which is represented by this plus symbol. So the unused and unhybridized p orbital remains vacant. Next, the stability of carbocation will be in a trend like this. The methyl carbocation will be less stable than the primary, and the primary will be less stable than the secondary, and the secondary carbocation will be less stable than the tertiary. So the tertiary is the most stable and the methyl is the least stable. So this order of stability can be explained by hyperconjugation and inductive effect. If you didn't check out our video on hyperconjugation and inductive effect, please check it out. I'll provide the link in the description below. We say that the tertiary carbocation is more stable because it has 10 hyperconjugative forms, and secondary only has 7 hyperconjugative forms, and primary only has 4 hyperconjugative forms. So the order of stability increases in a trend like this. Tertiary carbocation has more stability, the most stability. In terms of inductive effect, the stability can be explained by saying that there are 3 methyl groups present here in the tertiary butyl carbon, which are the electron releasing groups, which disperses a negative charge on the carbocation to the great extent in this tertiary butyl cations, and the dispersion of negative charge is less in case of isopropyl carbocation, since there are only 2 methyl group present which is attached to the carbocation, and in case of ethyl carbocation there's only 1 methyl group which is present, so the dispersion of negative charge will be less in case of ethyl group. And when we consider methyl group, there's no such dispersion occurs in case of methyl. So the increasing order of stability will be like this, which is methyl will be less stable than ethyl, and ethyl will be less stable than isopropyl, and isopropyl will be less stable than tertiary butyl cations. The next intermediate is carbanion, in which the carbon has a negative charge and 3 bonds attached to 3 atoms or group of atoms. We also have a lone unshared pair of electrons located in the p orbital of this carbon. So the central carbon here is sp3 hybridized. Now let's look at the formation of an carbanion. Consider the reactions in which acetaldehyde CH3 CHO acetaldehyde reacts with a base OH minus. Now this base abstracts an hydrogen, abstracts a proton, to be specific, abstracts a proton, and water molecules released, and these 2 bonds, which is here and here, which belongs to hydrogen, reside in the p orbital itself. So we get a carbanion CHO and a lone pair which is represented using a negative sign. So this carbon here is sp3 hybridized, which is represented by carbon in its excited state again. So in the s orbital we have 1 electron, and we have 1 electron in each px, py, and pz orbital. These three atoms here, here, and here will make a bond with these electrons here, here, and here. And since this H plus is subtracted by OH minus here, we have another electron residing in one of the p orbital. So we have a lone unshared pair here. And that's why this carbon here is sp3 hybridized. Remember that even lone pair will take part in hybridization. And the bond angle of this molecule will be 109.4 degree, whereas in a typical methane molecule, the bond angle will be 109.5 degree, and due to the bond pair lone pair repulsion, the bond angle is slightly reduced to just 0.1 degree, which does not make a big difference. So the tetrahedral structure of sp3 hybridized compound is retained here also in carbanion. Now let's check out the three-dimensional structure of a carbanion. This here is a three-dimensional structure of a typical carbanion, in which the bond angle will be 109.4 degree, not 5 as given here. To be accurate, it is 109.4 degree. The three bonds in the carbanions are attached in this fashion, like here. One bond towards us, one bond away from us, and one bond on the plane of the paper. And don't think that, please don't misunderstand that only the bond angle between these bond is 109.5 degree, and the bond angle is different when we consider these two bonds here, like this. Let me try to show. Even the bond angle between these two bonds will be 109.5. The bond angle between this and this bond, which is in the plane of the paper, will be 109.5, and the bond angle between this bond and this bond, which is in the plane of the paper, will be 109.5. And the two electrons are residing in the hybridized p orbital here. So when a proton like this, when it comes and attacks this carbanion, and the negative charge in here will be gone. The hydrogen will make a bond with this molecule. Next, let's see about the stability of carbanions. The tertiary carbanion is least stable, and the methyl carbanion is the most stable. This order of stability is just reversed when we consider the stability order of carbocations, and this trend can be explained using inductive effect. Since we have three methyl groups in tertiary carbanion, which are the electron releasing or electron donating group, it will destabilize the tertiary carbanion to a large extent than secondary and primary, since we have only two methyl groups in secondary and one methyl group in primary. It will destabilize to a large extent in case of tertiary carbanion. And this is the stability order of carbanions from alkenes and alkynes. As we can see here, the percentage of S character of this carbanion is 50%, and the percentage of S character of this carbanion is 33.33%, and the percentage of S character of this carbanion is 25%. So when S character increases, the electron will be close to the nucleus, resulting in lowering of energy, so the stability increases. And that's why the alkyne carbanion is the most stable in this case. The carbanion in which the unsaturated bond is situated at the alpha position to the unshared electron pair has an enhanced stability due to resonance. Here we can see the unshared electron pair, and the double bond is situated at the alpha position to this unshared electron pair. This is an allyl carbanion, and we also have benzyl and acetonyl and nitromethyl carbanion of these kinds. So these species show enhanced stability due to resonance, and we can also see the resonance structures and resonance hybrid of these compounds. In dimethyl and trimethyl carbanions, resonance stabilization would be even more produced than benzyl carbanion. So the trimethyl carbanion is more stable than the benzyl carbanion. But this trimethyl carbanion is less stable than acetonyl and nitromethyl carbanion, as we saw before. Acetonyl and nitromethyl carbanion show greater stability due to the electronegative atoms, which are in here. In the case of acetonyl, we have oxygen here, and in case of nitromethyl, we have nitrogen here, which are more electronegative than the carbon atom. And that's why the stability of acetyl and nitromethyl carbanion is more when compared to even triphenyl methyl carbanion. Next, we'll see about carbenes. Carbene is a highly reactive, highly unstable molecule containing a neutral carbon attached to two other atoms or group of atoms. It has two unshared electrons, so the valence electron of carbon has 6 electrons in total. As we can see here, two electrons are here and the other 4 electrons will be here. So it has 6 electrons in its valence shell. Now let's see the formation of carbene. When diazomethane, which is CH2 N2, N triple bond N. So nitrogen has a positive charge and carbon has lone electrons, so it has negative charge. When this is subjected to sunlight, we get a carbene CH2 and we have a lone pair plus nitrogen gas. This carbon in the diazomethane is sp3 hybridized, which can be shown by carbon in its excited state we have a lone pair of electrons here, so we can put those electrons here and 3 other electrons as usual. So we have 2 hydrogens here, so hydrogens will be bonded like this, and we have a nitrogen attached, nitrogen group, which is N2 attached here. So these 3 ligands make a bond with this central carbon atom. In this reaction, next what happens is that this bond will be taken away by this nitrogen, so we can erase this nitrogen. So this is the carbene we have here. This carbon here is sp2 hybridized, so we can draw the structure like this. Two covalent bonds are attached to hydrogen, and one hybridized orbital will be like this, another will be like up and down. So in this hybridized orbital, we have both the electrons with the opposite spin, which is shown here, and 2 other orbitals make a covalent bond with hydrogen, and one of the p orbital is vacant as shown here. This carbene is an interesting molecule since we have a lone pair and a vacant p orbital. This carbene can act both as a electrophile and a nucleophile. Now, carbenes have 2 possible structures, namely singlet and triplet carbenes. In singlet state, carbon atom is sp2 hybridized, in which one of the sp2 hybrid orbital contains the unshared pair of electrons with opposite spins, and the 2 sp2 hybrid orbitals form 2 covalent bonds as shown here. The 2 sp2 hybrid orbitals form covalent bond, and one sp2 hybridized orbital contains the lone pair of electrons with opposite spins. So this is a example of singlet carbene, and to note that the remaining p orbital is vacant like this. And the carbon atom in triplet carbene is sp hybridized, so it has nearly a linear shape. The 2 sp hybridized orbitals are used in the formation of 2 covalent bonds, as we can see in this structure here. The 2 hybridized sp orbitals form 2 covalent bonds with the alkyl groups, and the remaining 2 electrons with the same spin occupy 2 mutually perpendicular p orbitals. Whereas in the singlet carbene, they occupy the same orbital with the opposite spin, but here we have the electrons occupying the mutually perpendicular p orbitals with the same spin. Now let's take a quick look at the 3-dimensional structure of singlet and triplet carbenes. This here is a 3-dimensional structure of singlet carbene. As we can see here, one bond is towards us and one bond is away from us, and the bond angle is 120 degree. Nearly 120 degrees. Because of the lone pair bond pair repulsion, it may decrease, and we have 2 lone pair of electrons in the hybridized p orbital, and one unhybridized p orbital is vacant. But in the triplet carbene, as we can see here, Both the electrons occupy two mutually perpendicular p orbitals, unhybridized p orbitals, and both the electrons are in the same spin, as we can see here. Next, we can compare this stability of singlet carbene and this triplet carbene. Triplet carbene is more stable than singlet carbene because in singlet carbene we have this lone pair bond pair repulsion, so there will be an angle strain in this molecule, and such kind of strain will not be present in this triplet carbene. Since we don't have any lone pair bond pair repulsions in this triplet carbene, we don't have any strain in this kind of triplet carbenes, and that's why triplet carbenes are more stable than singlet carbenes. But when the carbon in this kind of carbene is attached to a halogen groups like this, chlorine, another chlorine here, instead of alkyl or hydrogen group, if the carbene is attached to a halogen group, then the stability order gets reversed. The singlet carbene is more stable than triplet carbene, given that the carbon must be attached to halogen group like this. This happens because of back bonding, which is we have a vacant p orbital in here, and we have a hybridized p orbital in which we have the two electrons of opposite spin. And since chlorine is an electron rich substance, it will try to make bond with these vacant p orbitals here and here. And due to this back bonding, the strain experienced by the molecule will get decreased and the stability will get increased. So whenever a carbon in the carbene group is attached to a halogen atom like this, the singlet carbene will be more stable than the triplet carbene. Since in triplet carbene we don't have such strain. One p orbital will be like this, and the other p orbital will be perpendicular to this p orbital, and each has electrons of same spin, and no back bonding can occur in these kind of triplet carbenes. So triplet carbene is more stable than singlet carbene if the carbon is attached to alkyl groups or hydrogen groups, and the opposite scenario, which is singlet carbene is more stable than triplet carbene. This will occur when the carbon in the carbene is attached to halogens like this. Next, we can see about benzyne intermediate. Benzyne is the simplest and the first homologous of arine type compounds, whereas an arine is a hydrocarbon derived from an arene. Now this here is a structure of benzene. And we know that each of these carbons are attached to a hydrogen. Now if you replace these two bonds which are attached to hydrogen with a third bond like this, then this compound here is a benzyne compound type compounds. Now let's see how this molecule was discovered. When a normal alkyl halide like chloromethane is treated with a nucleophile like NaOH, the product, which is methyl alcohol, can be obtained at normal room temperature, and of course a NaCl molecule will be released as a byproduct. So when alkyl halide is treated with a nucleophile like NaOH, the product will be obtained at room temperature. But when an aryl halide like chlorobenzene, now this aryl halide does not react with the OH minus nucleophile or any nucleophile at room temperature. Now this reaction proceeds only at drastic condition, which is heated to 300 degree Celsius at high pressure. Only then we can get the product, which is phenol OH here.